Today we will start a new chapter, moving charges and magnetism. Magnetism and electricity were known to scientists some 2000 years back itself, but their interrelationship was known only some 200 years back. In the beginning of 19th century, experiments performed by scientists showed that a magnetic field is produced by a electric charge in motion. A.P.Second is the scientist. While performing an experiment in a school, he found the magnetic field being produced by a current carrying conductor. So, A.P.Second's experiment. A straight current carrying conductor, he observed that while carrying current, deflected the magnetic needle kept nearby it. So, suppose this is the magnetic needle, this is south pole, and let's suppose this is north pole, this is south pole. So, when it is brought nearer to this current carrying conductor, so the north pole deflected like this. That is in the direction in which you curl your right hand fingers, keeping the straight current carrying conductor carrying current in the direction of the thumb. So he observed that the magnetic field around this current carrying conductor formed concentric circles which represent the magnetic field lines. So if you place the position of the north pole around this straight current carrying conductor, so you will get a concentric circle or a circle around this conductor with the conductor at its center. So the deflection path of the north pole can be shown like this, like a circle. So it is like this. So we can imagine that there are several such circular paths around this current carrying conductor. So these concentric circles with the conductor at the center, they represent the magnetic field lines. So using your right hand thumb in the direction of current carrying conductor and curving the fingers like this, that will be into the board, you will get the direction of the magnetic field. So, after this A.P.Second, the experiments performed by Ampere and others gave the idea of magnetic force acting on a charge moving in a magnetic field. So, just like an electric field, which is a vector field, a magnetic field is also a vector field which will exert a force on a charge only when it is in motion. So, the experiments performed by scientists is given in the form of an equation by Lorentz. So, according to Lorentz, if your charged particle is moving in a magnetic and electric field simultaneously, then it will experience a force which is given by Q into E bar. This is the electric force, and you know electric force is a function of position of the point from the source of the field, plus Q into V bar cross B bar. And you know this magnetic field is also a function of position. Now, the source of a magnetic field is here an external magnetic field, not generated by the charge that you are considering here. the charge here we are considering is in an electric field and also simultaneously in a magnetic field. So both the fields are applied simultaneously. Then it will experience an electric force. So let us represent it like this. And this we call this as magnetic force. So this force is known as Lorentz force. And we can call that as magnetic force. Now, this magnetic force, if you observe, Q into V bar cross V bar is a force which is vector product of velocity of the charge in the magnetic field and the magnetic field strength. So, the magnetic force depends on the velocity of the charged particle, whereas you see the electric force doesn't depend on velocity. So, the magnetic force acting on a charge depends on velocity of the charged particle and also on the magnetic field at the point where we are considering the charge. Secondly, suppose the velocity of the charged particle is parallel to the magnetic field direction or anti-parallel to the field direction, then the magnetic force will be zero. Why? Because we know V bar cross V bar. If you take the modulus value V sin theta, where theta stands for the angle between the directions of velocity vector and magnetic field vector. So therefore, this will become zero if this velocity is parallel to the magnetic field direction or anti-parallel to the magnetic field direction. And another point regarding this magnetic force is the force can be observed only when the charge is in motion. When the charge is not moving, if the velocity is zero, then automatically the magnetic force is also zero. And another point regarding this is, if the force acting on a positive charge is in one direction and the force acting on a negative charge will be in the opposite direction. So, it depends upon the direction of this force, depends upon the type of the charge or nature of the charge. On positive charge, if the force is in one direction, then on the negative charge it will be in the opposite direction. So these are some of the important points regarding this magnetic force. Now, to know the direction of the magnetic force, so we can say like this. Suppose if this is the magnetic field direction V bar, and suppose this V bar is the velocity vector. So that is say x-axis. Say this is y-axis. Then your magnetic force will be perpendicular to the plane xy, such that you can imagine the direction of the force using the right hand thumb rule. That is V bar cross V bar. So like this, it will be in this direction. That is V bar curling in the direction of V bar. So that is right hand thumb rule. So your velocity vector will be in the direction of, that is the magnetic force will be into the plane of the pole. As per this figure, if V bar and V bar are in xy plane as shown, then F bar will be in the plane perpendicular to this xy, but the direction will be given by the right hand thumb rule and it will be into the plane as shown in the figure. So in that way, using right hand screw rule or right hand thumb rule, we can find out the direction of the magnetic force. And you must remember that this magnetic force is a vector force. Therefore, you can apply the superposition principle due to several sources of magnetic field. The force exerted on the moving charge is given by the resultant force due to individual sources of magnetic field. So therefore, by applying the superposition principle, you can find the resultant magnetic fields due to several sources of magnetic field. So because it is a vector, the magnetic force is a vector. So just like electric field, magnetic field is also a vector. Now, we can make use of this formula to define or the relation. We can call that as a magnetic force or Lorentz force to define the unit of magnetic field. Suppose if the magnetic force is say 1 Newton and the charge is say 1 Coulomb, such that the velocity with which the charged particle is moving is 1 meter per second, then the magnetic field is given by 1 Newton second per Coulomb meter. So 1 Newton second per Coulomb meter from this formula. So therefore B is equal to, dimensionally we can say that B is equal to F by QB. So you know force is in newtons, Q is coulombs, velocity is meters per second. So that second goes to the numerator. So 1 Newton second per Coulomb meter is said to be 1 unit magnetic field, which is defined as 1 Tesla. So a magnetic field exerting this much of force on a charge in motion, on a charge of 1 Coulomb moving at a speed of 1 meter per second is defined as 1 Tesla. Actually, Tesla is a very big unit. So, for example, the Earth has a magnetic field whose strength is equal to 3.8 into 10 power minus 5 Tesla. So this is the horizontal component of Earth's magnetic field value. In some books it is given as 3.6, so nothing wrong with it. Since Tesla is a big unit, smaller unit, Gauss, is defined. So in terms of Gausses, so that BH value is taken as 0.38 Gauss. That means 1 Gauss is equal to 10 power minus 4 Tesla. So many Tesla is considered as 1 Gauss, and in Gauss units, this is the magnetic field strength of the Earth. Whereas the magnetic field strength of a neutron star, a star almost in the dying condition, in which the whole matter will be in the form of neutrons. So such a neutron star will have a magnetic field of strength nearly 10 to the power of 12 Tesla. Similarly, the nerve fibers in the nerves of our body carries the signals in form of electrical signals. So these electrical signals passing through our nerves also produces a magnetic field, a very, very weak field of the order of 10 power minus 10 Tesla. Okay, so from this very large value to some very small value, we can think of the strength of the magnetic field. But for Earth, because we can observe the magnetic field of the Earth with the help of a magnetic needle. But of course, the magnetic field strength of the earth is also very weak. Okay, so that is the 10 power minus 5 Tesla as the order of Earth's magnetic field. We generally consider the horizontal component. The vertical component won't show effect on the magnetic needle on the surface of the earth, and we consider generally the horizontal component of the magnetic field of the earth. So that is about the magnetic force. Another important point, when I said that the current carrying conductor, here we consider the current direction as the direction in which the positive charge moves. So remember, conventional current direction means the direction in which the positive charge moves. So that is the conventional current direction. Okay. Actually, in solids, electrons are the conductors. So the electrons move in a solid. So that is the actual current direction. But we consider the opposite direction of that electronic current as the conventional current direction. So whatever formulas or rules we discuss in electricity and magnetism, we consider always the conventional current direction. When I use the right hand thumb rule to know the direction of this magnetic force, so here also the thumb shows the conventional current direction, or the direction is the positive charge moves. So we assume that conductors carry positive current and we apply this rule. But the direction is exactly opposite to the electronic current direction. Okay. So next we will discuss about the force acting on a current carrying conductor kept in a magnetic field. This is a very important topic. The force acting on a current carrying conductor. Force on a current carrying in a magnetic field. Let us consider a straight conductor carrying a steady current I and is kept in a magnetic field. Suppose, so this is a conductor carrying a current of say some I and kept in a magnetic field. For convenience, we assume this magnetic field to be uniform. So, when current means the charges are moving, that means every charge in the conductor will experience a magnetic force. And let us assume that the area of cross section is say some A, and let L be the length of the conductor. Now, so according to our formula, the magnetic force is given by Q into V bar cross V bar. So let us assume that the direction of the magnetic field is perpendicular to the current direction, so that sin theta will become 1. And suppose you have you want to calculate the force on all such charge carriers, and then total force I want to know. So let us suppose this is a formula. So I want to calculate the total magnetic force on all the charge carriers in the conductor, so that a net force acts on the conductor due to this magnetic field applied on it. So the charge, let us suppose each carrier has a charge Q, and let N be the charge density, that is number of charges per unit volume. Then the volume term is A into L. So that is area of cross section into length. So N is the number of charge carriers per unit volume. Total volume of this conductor is AL, area of cross section to length of the conductor, and the charge of each carrier is say some Q. And you know, when a conductor carries electric current, the speed with which the charges move, we call it as drift velocity. So that is the average velocity. Let us say it is Vd bar cross d bar. And since we consider that to be perpendicular, you can find out, okay, let us keep that vector term also. Otherwise, N Q Vd, for the sake of easiness, let us drop that sin theta and let us represent this N Q Vd into A into L into B. And here, this quantity is nothing but the current density J. So, because in other words also, we can write, we can explain like this. We know Vd is nothing but NQ. Vd is, let us suppose V is the distance traveled in a time t, and say into A. So you know that the distance traveled per second is d. A is the area of cross section. This gives the volume per unit time. So this volume into number of charges per unit volume is n. Charge of each carrier is q. So this entire quantity gives the charge, total charge, that is passing per unit time. So the charge crossing per unit time, hence this must be the current. Therefore, NQVD into A. So actually this entire term gives the current, or this current, when you multiply with the area, divide with the area, then this quantity is current density I by A. So this is I by A, that is the current density J, and A, L, B. So we know this is the actually a vector in the electricity. This is the only quantity that has the directional property. That is the vector property. So G bar. So this together we can write it as current. So that is I L bar B. Here we put this in terms of vector. If you write, so you consider this I L bar as a vector, because actually length is not a vector. Since the quantity J, current density, has the vector property, so we transfer that property to the current element. This we call it as current element as vector quantity, and hence we can write like this. So in terms of vectors, we can write like this. So J bar AL cross B bar. If you want to write it in terms of vectors, so you can write like this. Or simply, since J is a vector, in vector notation, the force is given by F bar is equal to I L bar cross B bar. So here we assumed, for the sake of simplicity, that the direction between the magnetic field vector and the current direction as 90 degrees, and we eliminated that. So therefore, this magnetic force acting on the current carrying conductor is given by this formula. So how we did it? From this definition of magnetic force, the total charge passing through the conductor is given by this And suppose the drift speed of each charge carrier is v bar. So that is drift velocity, and v bar is the magnetic field applied. And in terms of magnitude, we have written it like this. And this quantity, as I explained earlier, will give you the current density J and A V bar. So since J is a vector, so I wrote the symbol. The symbol of vector is written over it. Hence, I have written vector symbol, that arrow over V also. So in terms of vector notation, we can write the magnetic force is equal to J bar AL into V bar. But J bar into A is nothing but current density into area is current. So we transfer this arrow, that is the vector direction, to the length. But only length is not the vector quantity. We call this as current element. So that current element we consider it as a vector, and we represent it like this. So this is the force acting on a current carrying conductor. Suppose if the magnetic field is parallel to the current direction or anti-parallel to the current direction, definitely you know the magnetic force is zero. So in terms of magnitude, the magnetic force is given by BIL sin theta. So using that formula, we can calculate magnetic force acting on a current carrying conductor. Okay.